Hello, everyone. Welcome to Talk to a Scientist. And today is a very special session for multiple reasons. One thing is we are talking about space, which is not something we get to do very often on Talk to a Scientist. And in space, we are talking about something which is a black hole. I mean, it's a black hole in space, quite literally and figuratively. So lots of questions have already started coming in about this. Second reason why this is extremely special is because we are joined by Dr. Abhijeet Borkar, who is an astrophysicist. So remember, we all grow up to saying we want to become astrophysicists. Well, Dr. Borkar actually did become one, who is an astrophysicist based in the Czech Republic. So can anyone type in the chat window, where is the Czech Republic? Is it in Africa? Is it in Asia? Is it in South America? Where is the Czech Republic? So that will tell you where Dr. Abhijeet is right now. Very good, Jayasurya. It is in Europe, and he works at the Astronomy Institute there. It's extremely inspirational to have him with us, and he's all yours for questions. So all those questions about black holes you wanted to get answered, this is the time. This is the time, guys. All right. So everyone is muted. Use the chat window to type your questions simply because there's too much background noise. We will stop every few slides for questions from you guys. And with that, I think that's it. Over to you, Abhijeet. You've shared your slides and we're all set. So let's get going.
Okay, excellent. Thank you so much. I'm really looking forward to interacting with everyone here today. So hello, everyone. My name is Abhijeet Borkar. I am a scientist here in Czech Republic. I work as a support scientist for one of the biggest telescopes in the world called ALMA, which stands for Atacama Large Millimeter and Submillimeter Array, which is a radio telescope that is currently operated by North America, Europe, and Asia together, and it's located in Chile, in South America. So it's one of the biggest telescopes in the world, and this telescope was also instrumental in finding out the first picture of a black hole that you see on top of the slides here, the amazing picture that everybody saw last year. That was a couple of years ago. It was in front of a page of every newspaper. So this telescope was the main instrument that was used to observing this image of the black hole. So today we will be talking about black holes. So all of you must have seen these amazing pictures of black holes everywhere. You might have seen them in newspaper articles, in your school textbooks, somewhere in Discovery Channel documentaries and so on. Or you might have seen this amazing image in the movie Interstellar, if you have seen that. So these are some representations of what black holes could look like that we have thought of. But exactly what are black holes? How do we know what they are and how do we find them? So today, my task here is to discuss with you how black holes are formed, how do we actually observe them, and what do we actually study about these black holes. So one of the things about black holes everybody knows is that they are black and there is no light coming out of them. So how do we exactly actually observe them? That is one of the biggest questions that we have. So today we will be studying and sort of trying to understand how black holes work. So to understand the concept of black holes, we must first have to understand the concept of escape velocity. So some of the oldest children here who are in their late high school, they will probably know about escape velocity. But to give the idea about escape velocities to younger people, imagine throwing a ball. So everybody, when you play cricket, you throw a ball up, and when you try to take a catch. So when you throw the ball up, it goes up, and then eventually it comes down. And the faster you throw it, the higher up it goes, but it will always eventually come down. But that is not the end of it. It depends on how strong the gravity is. And on Earth, we have a specific gravity of Earth. So we know how big the Earth is. And if we throw the ball fast enough, the ball will not come back. So if you are throwing something really, really, really fast, then the ball will not come back. It will just escape the gravity of the Earth. So gravity is something that we are every day used to. When you stand on the ground or when you leave a ball from your hand, you see the ball is getting dropped down. That is because of the attraction of gravity from the Earth. But that attraction is not infinite. It has a limitation. So once you provide enough energy to the ball to throw it completely out of the system, so you're sending it so fast that it will just eventually will not come back down. And that is what we do when we are sending satellites into the sky, and when we are sending astronauts to the moon. Of course, with our hands, we don't have that much energy, so we cannot just throw a ball so fast that it will leave the earth. But what we need to do is we need to burn a lot of energy. So we have these massive rockets with a lot of rocket fuel, and these rockets then are launched, and they are given this amazing large amount of energy that will give them high speed. And with this high speed, they are able to escape the gravitational pull of the earth completely. So that's how escape velocity works. So you have the gravitational pull from the earth or from any object. So if you have the sun itself has a gravitational pull. Moon, Mars, all of them have their own gravitational pull, which depend on the size of their body. So the moon is much smaller than our earth. So it has much smaller gravitational pull. So it's much easier for something to escape from the moon, while it's much more difficult to escape from earth. So the bigger it is, the more difficult it is to escape, right? So do you understand this concept of escape velocity? Can we get some questions about that?
Sounds good, Abhijeet. So Pooja asks, what is velocity?
So velocity is just another name for speed. So you can just think of it as speed. Velocity is a very technical term that is used when we are talking about something that has both magnitude and direction. But for some of the younger students here, they will learn that in their high school what velocity actually means. But you can just think of it as a speed. So it's just how much fast something is going.
All right. Lots of questions of black holes, Abhijeet, but I'm sure you'll get to them. The types of black holes. Is a black hole really black? We'll talk about that. But I had a question. When you said that the moon's gravity is less than Earth, is it that's why people, when they show astronauts on the moon, they're like bouncing around?
Yes, exactly. Okay. So when you're walking on Earth, we are used to walking on Earth's gravity, which is much stronger. While when you're walking on the moon, or when you see currently there is a NASA rover on Mars, and they also try to fly a helicopter on Mars. So because Mars has much smaller gravity and moon has much smaller gravity, you don't need a big sort of engine and big wings to the helicopter to fly the drone on Mars. So one of the things that is important to understand in the concepts of black holes is that the more massive something is, so how much mass something has, how heavy it is, and how big it is, these are the two important parameters to understand how much gravity something has. So Earth is quite big and it's made up of rock, so it's quite big and heavy, so it has a lot more gravity, while the moon is much smaller and it's also not as heavy as the Earth, so it's much lighter than the Earth. So it's much easier to walk on the moon. If you try to jump on the moon, you will jump much higher. Currently on Earth you can jump for like 1 or 2 feet in the air, but on the moon you can jump even higher.
Oh, sounds good. Sounds good. So we will all weigh lighter on the moon, Abhijeet?
Yes, you will weigh about 1/6 of what you weigh on Earth. So if you weigh 60 kilograms on Earth, you would weigh only 10 kilograms on the moon.
So henceforth, when anyone asks me this, I'm going to go with my moon weight.
Exactly.
I'm going to tell people my moon weight. That sounds very good. Wonderful start, Abhijeet.
Okay.
Abhijeet, again, so Nishchay, velocity, like Abhijeet said, is just speed. Let's go with speed. Okay, how fast you throw a ball or something. We'll come to more questions subsequently, Abhijeet. Yeah.
Okay, excellent. So the second concept that we need to understand. So first we learned about escape speed. So how fast something needs to be to escape the gravitational pull of the planet. But the other concept is that what Einstein has taught us in 1905 was that nothing can travel faster than the speed of light. So the speed of light is the maximum speed limit in the universe. No matter how fast you try to send something, it will never be faster than the speed of light. That's something that Einstein figured out, and we have confirmed that with experiments that no, nothing can travel faster than the speed of light. That is the maximum speed limit. So what does that mean is that imagine you have a star. And how do we see a star? We see a star because the star is emitting light. our sun is a star, and the sun is giving off a lot of light. So there is some chemical and nuclear reaction going on inside the sun, and the sun gives off a lot of light. So we see the bright light coming from the sun that gives us day and night cycles. So that light comes off because the light can escape the gravitational pull of the sun and reach us. But if you imagine something that is so big and so massive and so heavy that even light cannot escape the speed, escape speed of that object. So if you have a star that is so big that, similar to how you throw a ball up, if you shine a light up, the light beam will go up and it will come down again. So as I showed you here in the picture on the left, if you throw a ball up, it goes up and comes down, because when you're throwing the ball with your hand, it just does not have enough speeds to leave the gravitational pull of the earth. It will come back because of the gravitational attraction of the earth. Similarly, if you try to shine a light, if you have a laser beam or a flashlight, if you try to shine light on a very, very big star, if it is so big that the escape speed of that star is faster than the speed of light, then if you try to shine light, it will just try to go up. But because of the heavy, extreme pull, gravitational pull of that object, the light will just come back down. So what happens in that case is that you will just not see any light coming from that object. So essentially, what you need is to make a black hole is you need something really, really, really heavy. So I have just given an example here of a big mass, but this is not sufficient. What you need is something really heavy, and you need to compress it down really, really tiny. So the two concepts that we need are how heavy something is and how small something is. So if you have a big star that just keeps on becoming bigger and bigger, but it's very light in a sense that it does not have the density. So some of you have studied in school the concept of density, which is mass divided by the volume. So if you look at a big ball of cotton candy and big ball of stone, the cotton candy of the same size has much less weight compared to the big ball of stone, because the stone is much heavier, and in the same size of volume, it has much more mass. So that's what we call density. And to make a black hole, it's not sufficient to just have the mass. What you need also is very high density. And with that high density, you can create extreme strong gravity that will create a black hole. So what you need is something that is very, very heavy, and you need to compress it down to very, very tiny size so that the escape speed of that object becomes so high that even light cannot escape from there.
All right.
Is that concept
yeah,
understood?
I think they're getting it. So Abhijeet, we have to think of light as an object.
Yes.
Yes, you have to think of it like every light particle is an object, right? Mm-hmm. And the photon, or whatever you want to call it in physical terms, it goes up and it has to come down. So we don't think of light as an object. I think that's why we are finding it hard to wrap our head around light not coming back.
Exactly. So one of the interesting thing is that because the speed of light is so fast, it's 300 million meters per second. So in 1 second, the light travels 300 million meters. That's really, really far away. So it takes light only 1 second to reach to the moon, and the moon is really far away. So it takes really quick time. So in our day-to-day life, light seems instantaneous. So when you turn on a light, it seems like the light particle that is coming from the light bulb to you, it's coming instantaneously, but that's not the case. The light has a finite speed. Yes, it has a limit.
Yes, exactly.
It cannot travel infinitely fast.
So Abhijeet, Pooja has a question. What is the black hole nearest to the Earth?
So the nearest black hole is, we think, is in the Crab pulsar. So one of the black holes is about 1,000 light years away. So that is one of the stellar mass black holes that we have seen that form from a supernova event. So I will discuss exactly how do you make these black holes.
Okay. Any other questions? Abhay, do you see other questions? Athansh and all of them are getting the concept. I can see their comments are making us clear that they're getting the concepts. Rahit Singh asks, why can't nothing escape a black hole? But I'm sure you're going to come to that. Because black holes are famously known as this, they suck everything out of you, right?
Yeah. Exactly. Yeah, so the concept that I made in front of you right now. So the two important, so one thing you need to understand is that the escape speed, that for every object there is an escape speed. So for Earth, we have the escape speed that if you put something on a big rocket and give it a large amount of speed, it will go out of Earth and it will not come back. So that's how we send astronauts to the moon. Similarly, black hole also has this escape speed, but the problem comes is when you have a limit on how fast something can go. So when you are in a black hole, you need to travel faster than the speed of light to escape, because the escape speed of the black hole is more than the speed of light. But Einstein has told us that nothing in the universe can travel faster than the speed of light. So even if you try really, really hard, if you put as many rocket boosters to your rocket and your spaceship, you will just never reach the speed to overcome this escape speed of the black hole. So even if you tried, you will, similar to how a ball is thrown, you will try to go up, but you will eventually come back again. You will never be able to escape completely.
Oh, so that is why it is that thing that sucks everything in, because we can't break the light speed of light. Okay.
Exactly.
I think that answers a lot of questions. Okay. Maybe what do you think, guys? Should we move on? Take a few more questions? Lots of questions, Abhijeet. I mean, really, you're solving all our black holes, all our problems. Nirali asks a great question, Abhijeet. Maybe we'll take this and then go on.
Yeah.
If we release a feather, it takes more time to fall than a stone. Surely, a feather floats and falls and a stone just goes plop. So what will happen in a black hole between a feather and a stone? Will the stone be going first or the feather go in first? Great question.
Of course.
Yeah.
Excellent question. And this experiment was done also by the NASA astronauts on the moon. So one of the reasons the feather goes down so slowly, because Earth has atmosphere. So we have a lot of air. But if you do the experiment in a place where there is no air, then the feather falls exactly at the same time as the stone. And to think of it, it's more complicated to think of it in terms of comparing the feather to a stone. What you can think of it, if you have a tennis ball and a cricket ball. So a tennis ball is much lighter compared to a cricket ball, but both are similarly sort of round shaped objects. And when you drop both of them from the top of a building, they both will reach the bottom at the same time, because they are not affected by the air resistance that is present on Earth. But if you try to do the experiment on the moon, where there is no air, so moon has no air atmosphere around it. So if you try to drop a feather and a hammer or a rock, they both fall at the same time. And that will be the case also inside the black hole, that if you try to drop a feather and a rock, they will both fall at the same time. So on Earth, the difference is because of the atmosphere. The atmosphere, air currents and airflow creates a resistance to the falling of the feather.
Oh, that's fascinating to think of a feather and a hammer falling plop at the same time.
Anyway. Yeah, if you go on YouTube, you can find the video of the astronaut dropping both of them at the same time.
Oh, really? Okay. Yeah. That'll be interesting, guys. You can take a look. All right. We can move on, Abhijeet. The next round of questions.
Okay. So just to make it clear again, to make a black hole, what you need is something that is really, really heavy, and to make it really, really tiny and compress it. In theory, you could make a black hole out of anything. You could take the entire Earth and compress it really, really, really to the small size. Of course, you have to compress it so much that our Earth, which is 6,000 kilometers in radius, so it's about 10,000 kilometers in size. That's a big, big amount. And you need to squeeze 10,000 kilometers of Earth into a tiny ball the size of a marble. Can you imagine that? You have to take the entire Earth and you'll have to squeeze the Earth into a tiny size of a marble, so about 2 centimeters in size. And you would make a black hole out of the Earth. Or if you instead consider a human, you could take a person and you compress the entire person to the size of a virus, then that person would also become a black hole. But of course, thankfully, we just don't have any machines or no way of creating this kind of extreme squeezing down of objects. That doesn't exist. So we cannot really squeeze down Earth or persons or anything that we see every day to squeeze them down to a black hole. But nature is different. In nature, there are situations where this thing happens. So there are some big stars. So these stars are called very big supergiant stars. So they are 20 times bigger than the sun. So they are 20 times massive than our sun. And they are so big that they are bigger than our solar system. And what happens is that in a star, there is a balance. The outer layers of the star are pushing everything down because of the gravity of the star. So the outer layers are pushing down and they're trying to collapse inward, while the radiation that is coming from, so the light that the stars are giving out from this nuclear reaction, that is pushing everything out. So if you can imagine, when you are standing next to a table fan, the air is pushing out your hand, right? Similarly, the radiation that is coming, the light that is coming from inside the star, that is pushing out all the material, all the gas that the star is made up of, that is pushing everything out. And the gravity of the material itself is pushing everything in. And what happens is that as the star gets older and older, it uses up all of its energy. So just how when you're driving a car, you have to put in petrol. And once you run out of petrol, your car stops. Similarly, a star runs on hydrogen. So what the star does is it burns hydrogen and creates helium. And that's how it creates this radiation, all this energy to sustain the lifestyle of the star. And at the end of its lifestyle, what happens is that it runs out of its petrol, which is hydrogen. And once it runs out, it can no longer create this radiation that is pushing everything away. And it has to essentially left with nothing else. So what happens is all the material that was trying to push everything in and the radiation that is pushing everything out, it used to be in a balance. But now as the petrol is over, the balance is gone and everything just crashes down completely. And what happens is that as it crashes down, it throws out the outer layers in a big explosion that we call a supernova, where all the outer layers are thrown out while the core of the star gets compressed under its own gravity. The mass is so heavy that it just falls and compresses so much that it eventually turns into a black hole. So that's how we know a black hole is formed. So this is how, so what you need is a really big star that is 20 times bigger than the sun. And once it ends its life cycle and it runs out of its petrol, it has this massive explosion where the outside of the star is completely thrown out while the inside is completely crushed into a tiny sphere. And that tiny ball becomes a black hole. So that's how black holes are formed. So I guess we can take a couple of questions right now.
Absolutely, Abhijeet. That was a very interesting explanation. I think we all got it. Abhay, you want to take some questions?
Sure. How do we weigh black holes? How do we weigh a black hole?
Excellent. So that is a fantastic question. And that is difficult to answer in a sense that we have certain ways of knowing the mass of something. So some of you might have studied the Newton's laws of gravitation, right? F equals m1 times m2 divided by r squared. So the force of gravitation is proportional to the two masses and inversely proportional to the radius. So what we do is we actually observe these black holes which are in a pair. So that is something that I will come to in just a moment, how that looks like. So what we call these are binary stars, where there are two stars orbiting each other, similar to how our Earth is going around the sun. In the same way, there are stars which are going around each other. And when one of those stars ends its life and forms a black hole, you have one black hole that is being orbited by another star. And by measuring the orbit of this star, we can calculate how massive the black hole is. So we use the Newton's gravitational law and what we know as Kepler's laws of motion. So some of these in your 9th or 10th grade you will learn, or maybe in the 11th grade, these Kepler's laws of motion. Using those equations, we calculate the mass of the black hole.
Oh, fascinating. So your mass is calculated by its effect.
Exactly.
Pretty much on the other star.
Yes.
Okay.
So if you just have one single black hole that is not surrounded by anything, it's really difficult to measure its mass.
Correct. Absolutely. So Abhay and Abhijit, Dhruti has a good question. Abhay, do you see that?
Okay, it's one of the
She said,
recent ones because
uh, she
yes,
said,
because I'm at the ones that are from like 2 minutes
no, no
ago.
problem. She says, is it possible for our sun to turn into a black hole? If a supernova event happens or something, can our sun become a black hole?
Thankfully not. Our sun is just too small. As I mentioned here,
Ah,
you need this the star to be 20 times bigger than the sun. So it has to have not only the big size, but also a lot of mass. And our sun just does not have a mass to make a black hole. It's just too small. Our sun is one of the smaller kinds of stars. Uh,
oh
what will
my God.
happen to our sun is our sun will eventually in 5 billion years will grow to be this red giant star, and eventually it will become a white dwarf
Hmm.
object, which is a different kind of object compared to a black hole.
Okay,
To
but
make a
not a
black
black
hole you
hole.
really need big extremely big stars.
All right. Wow. Abhay, you want to take Nirali's last question?
Yeah, actually, yes, I'm just finding it.
It's a last question.
Yes, what's inside the black hole?
We will come to that at the end. I will come
Okay.
to that question
Okay.
towards the end. So we will first discuss how we observe them so that we get to know what is really what we understand, and then we will come to things that we don't really understand.
Sure. Then we can go on, I think. Abhijit.
Okay.
Yes.
Okay. Sure. Can we do one more question?
Sure, sure.
How much time does it take to make a black hole?
Aha. That is a fantastic question. So usually a star lives for a very long time. Our sun will live for total 10 billion years. That's a very long time. The sun has been around for 5 billion years already, and it will live on for another 5 billion years. But some of these big stars, they don't live that long. Although it's still quite long from human time scale. We live only about 80 to 100 years. But these massive stars, they will live only for about 10 million years, 20 million years. So that's still 1,000 times smaller time span than our sun. But the transition that happens between a star becoming a red giant and turning into a supernova and turning into a black hole, that happens in a fraction of a second. So
Oh,
in the core,
wow.
when
Okay.
the fuel runs out, it's a matter of a second that the entire star just goes supernova and compresses everything down and turns everything into a black hole. So you can imagine the star living for millions of years, and then suddenly in one day it just vanishes
It,
into a massive explosion and then a black hole.
oh my God. Quite an extreme, Abhijit, to have
Yeah,
existed for millions of years and disappear in seconds.
exactly.
All right. Fascinating, huh? Your everyday job is fascinating.
Yeah.
All right. We can go on. Lots of
Okay.
questions, but we'll come to them, Abhijit. Yeah.
Yeah. So as I was mentioning, one of the ways we can study these black holes is when we are trying to understand these stars in a binary. So what happens when you have a binary system? So I will play this picture. So you have a black hole in the center, and it's surrounded by a star. And this star, the outer layers of the star get sucked in by the gravitation of the black hole. So if the star gets too close to the black hole, then it gets completely torn apart and all its material is taken over by the black hole. And this creates, as you're seeing in this video, it creates this disk of material that is going around the black hole. Can you see that? So
Yes, yes, we
as
see
you
that.
will see in the video, you will create this disk of material that is around the black hole, and that starts shining. So what happens is that any material, so when you are in winter and your hands are really cold, you rub them really fast, right? And what happens when you rub your hands is your hands get warm. So that's what we call friction and heating because of the friction, right?
Yes.
So similarly, this material that is going around the black hole, that is also made up of tiny particles, and those particles start rubbing against each other, and that creates friction, and
Yeah.
that heats everything up.
Oh, so that's the explosion that happens.
Yes, so the bright light that you're seeing is the material that is forming this disk around the black hole that is heated up to so high temperatures that it seems like it's burning bright.
Oh,
And what
wow.
we measure from the black hole is actually this light coming from this material that is surrounding, forming the disk. So this disk is called the accretion disk of a black hole. So what we are when we say that we measure or we see a black hole, we are not seeing the black hole itself. So the black part in the center, what we are seeing is the signature of this extremely hot material around it. So this material is glowing so high that it's millions of degrees Celsius. It's
so
not
just to clarify, Abhijeet, that hole was the black hole, and that star, that flame, was the star being sucked into the black hole.
Exactly.
Okay. And as it was, the particles friction caused the heat generation.
Yes.
Oh.
So you have a lot of these particles which are made up of the star material. So it's mostly hydrogen, and the hydrogen atoms will bounce against each other and crash into each other when they are going around this black hole in this environment, in this disk. Wow. And that friction, that interaction between these particles, that will create a lot of heat. And the disk is then heated up to millions of degrees Celsius.
Oh, fantastic.
And that extreme high temperature, so as you know, the hotter something is, the brighter it burns. And this burning is what we see as in the form of accretion disk. So that is what we observe in a black hole. So these are what we are called as X-ray binaries, because they are stars in a binary. So it's not always that the entire star will be ripped apart and sort of accreted. In most of the cases, the star is still further out. So it's not completely ripped apart, but what happens is that some outer layer of the star will be pulled in by the black hole, and that small amount will create this accretion disk. So the star will still be stable. So it will keep going around the black hole, while the black hole will start stealing small and small amount of the material from the star. And that will keep creating these accretion disks. And we keep seeing that, and especially because it's so hot, it is not only seen in normal light, but we also see it in X-rays. So we have these massive X-ray telescopes in the space, and we see X-ray radiation coming from these objects. And these are some of the brightest objects in the universe. So we see those X-ray coming from the accretion disk, and that's how we observe these black holes.
So Abhijeet, these events are constantly happening in space?
Yes.
These star parts getting sucked into black holes and...
Exactly. So because in a galaxy, there are 100 billion stars. And out of them, many of them have turned into a black hole. So in our galaxy, there are almost 1 billion black holes.
Okay,
and
wow.
We see some of them activated like that, forming the accretion disk. So we are constantly seeing many of them all over our galaxy. So we are constantly seeing them. If you look at this part of the sky, if you look at that part of the sky, you will keep on seeing. What you need are X-ray telescopes, and really amazing telescopes to see them.
Okay, sounds good. Okay, we can move on. Sure.
Yeah. And then this, let's see if I can go to the next slide. So the second way of observing the black hole that we started doing that only very, very recently is from merging of the two black holes. So instead of having one star orbiting a black hole, what you can have is both the stars going supernova and ending up as black holes. And when they are orbiting each other, they give off this radiation that is in the form of gravitational waves. And you're seeing is the simulation of two stars which are going around each other and forming this spiral out. And this kind of the spiral dance that they are doing around each other, that is what we observed in the form of signal coming in gravitational wave detectors. So you might have heard a few years ago, the LIGO observatory in America that discovered the gravitational waves. So here we were seeing the simulation of a different kind of object called the neutron star, which is another kind of end point of life of a star. But similarly, when you have two black holes orbiting each other, they also give off these gravitational waves. And what we measure are the fluctuation of these two objects going around each other and measuring the gravitational waves. So similarly, if you can think of a nice lake and you throw two stones into the lake, they create these small waves in the lake. And when the when the two waves from two objects thrown come together, they form these spiral shapes. So similarly, you can think of the space as a lake in which the black holes are existing. and the interaction of the black hole creates these waves, and we can measure these waves that are coming towards Earth. And by measuring these waves, we can see that what type of the black holes they were. By measuring how big the waves are and how spread apart the waves are, we can measure, because understanding the similar example, if you are throwing a big rock into the lake, it will create much bigger wave. While if you throw a small rock, it will just create a small wave. Similarly, if you have a big black hole or two big black holes coming together, they will create really big waves. While if you have two small black holes coming together, they will just create two small waves. So that's one of the other ways we discover black holes in the universe.
Abhijeet, what we saw was two black holes coming together, basically.
In this video is not black holes. So because they are two stars, they are neutron stars. They are a different kind of object. They're similar to black holes, but they are not completely black holes yet. But the example is quite similar. So you can just imagine, instead of these two stars, imagine two black holes.
Oh yeah, you can see their gravitational forces now. Yeah, and then you see some supernova event happening very
so
soon.
in the case of neutron stars, because they are not formed into a black hole yet, they have still material remaining that can form a supernova. While when you have two black holes which merge together, there is no light, because there is no light coming out of the black holes. So you don't see any light signal, you don't see any supernova. What you see only is the gravitational wave signal.
Fascinating. I mean, I think all of us were like completely blown apart, pun intended, by this video.
So we can take a couple of questions if there are right now.
Sure. Anika wants to ask. Abhay, you want to ask that?
Yes. Actually, right, yes. Is it possible to invent a gadget that can take you in and out of a black hole unharmed?
Unfortunately not. As I mentioned, nothing can, once you go inside the black hole, nothing can come out. So no matter what kind of gadget you build, it will just never come out. So there is no way of going in and out. You can always go in as you wish, but you will never come out. That is the main problem.
You know the saying, right? Angels fear where fools rush in where angels fear to tread.
Exactly.
Kind of situation. Oh my God. Pooja asks, are there different kinds of black holes?
Yes.
We'll talk about that. Okay.
Yeah, just the next slide will be talking about the black holes.
Sure.
Can I ask one more question?
Mm-hmm.
If you get sucked into a black hole, will you die?
Yes. In fact, especially in the case of these star-type black holes, which form from the end of the stars, they are so big and so in fact, they are quite small. And because they have a lot of these material going around them, the likelihood is that you will actually end before you even enter the black hole, because this material that is surrounding, as you can see in this picture on the left, this material is extremely bright. So you know how when you hold your hand on a light bulb, you feel the heat of the light bulb, right? Or if you're close to a fire, you see the heat of the fire. But if you get too close, your hand gets burnt. Now imagine a fire that is burning millions of degrees Celsius. That is so bright and so energetic that if you get any close to it, you will get completely burnt. So even before you fall into a black hole, that will be the end. But if you somehow survive that, once you fall close towards the black hole, the gravitation of the black hole is so much that what will happen is that your legs will be pulled much more than your head, and you will be completely stretched like a spaghetti.
Oh, that's why they're called spaghettified in a black hole. Okay.
Because the gravitational pull depends on your distance from the center, right? So your legs will be closer to the center of the black hole compared to your head. So this difference between your head and your legs, that is just too far. On Earth, that is not a problem because Earth is too big. Earth has a radius of 6,000 kilometers. So another 2 meters of height on 6,000 kilometers doesn't make much difference. But as I mentioned, the size of the black hole formed from a star will be only 1 kilometer or even much smaller than that. And when you're especially inside the black hole, you're very, very close to the center. Yeah. And there, even a difference of 1 or 2 meters will make your legs will feel 2 times or 5 times more gravitation than your head. So you will essentially get stretched and stretched until, like a rubber band, you will be stretched until you are snapped.
Okay, Abhijit, Athansh had a question. What's the difference between a black hole and a wormhole? And Dipti asked, what is a white hole? So black
Yeah,
hole,
so
wormhole, white hole.
yeah, those things I will come at the end
Okay,
about the
okay.
things that we don't know.
Sure, we'll go ahead then. Let's go ahead.
Yeah. So the other question that was asked is what are different kinds of black holes? So the ones that I was describing to you before so far are what we call as stellar mass black holes, because they are stellar as in made up of stars, and their mass, or their how heavy they are, is about few times the size, the mass of the sun. So they can be from 3 to about 100 times the mass of the sun. So these are what we call small. I mean, they are quite big. They are 100 times or 20 times or 50 times as massive as the sun. So that is still quite big. But those are still much smaller compared to the other kinds of black hole that we know. And those we call supermassive black holes. And we don't just call them massive black holes, but supermassive, because they're not just 5 times, 10 times, 100 times massive than the sun. They're millions to billion times the mass of the sun. So they're really big. They're unimaginably big. It's just difficult to understand, because for us, it's not easy to understand what millions and billions means. They're just so big that they are not made up of just few stars who have ended their life and have become black holes. They are made up of billions and billions of stars. And where they live is, they live in the centers of the galaxy. So you have the galaxy, which is made up of 100 billion stars. And at the center of every big galaxy, there is a big supermassive black hole. Of course, I'm showing this a cartoon image of the galaxy. So this is not a real picture. This is a cartoon. And in the center, there is a black circle. Again, that is not to the scale. A supermassive black hole is not that big compared to a galaxy. Even that black hole is much smaller compared to the entire size of the galaxy. But it's so heavy that it has influence on a lot of the stars and gas in the galaxy. So this is the second type of black holes that we know. And of course, there are some black holes which are in the intermediate type. So between 100 to million times the mass of the sun, those we call as the intermediate type black holes. But those are something that we think exist, but we have never found them. While we have already, I showed you the videos of how we see the stellar mass black holes, and I will now show you how we observe this supermassive black holes. So these are the two types of black holes that we have already seen in the universe. So to compare how big a black hole is, a supermassive black hole is to a galaxy, is imagine a virus to a person. So a virus is so small that we cannot see it. You need a really powerful microscope to see that. So it's really tiny, but a virus has so much influence on our body. So when we get a cold virus, our entire body reacts to that, right? Similarly, a black hole, a supermassive black hole at the center of the galaxy is really tiny. You really need extremely amazing instruments, amazing telescopes to see those black holes at the centers of galaxies. But they are so powerful that they have an influence on the entire galaxy. So this is how the sort of the supermassive and stellar massive black holes work. So the question is, how do you find these supermassive black holes? And one of the ways is to look at our own galaxy. Is there a black hole at the center of our own galaxy? The answer is yes, but how do we know that? Because when we look towards our sky, we see the Milky Way band. Have you guys seen the Milky Way band in the night sky? If you go out on a very dark night, sometimes if you go, especially in the forest, or if you are going hiking at night, you might see this band of milky belt in the sky. That is the Milky Way. And when you look at the center of that, unfortunately, we cannot see much because the center is actually obscured by a lot of dust. So that is a space dust, a lot of gas and a lot of material that is present between us and the Milky Way, because we are seeing through the disk of the Milky Way. So we cannot see it in normal light. But what you can do instead is, instead of looking at it through normal light telescopes, you can look at it through infrared and radio telescopes. And when you look at the center of the galaxy through radio telescope, you see this extremely bright object in the center. So this central part of this image you see, that's the center of our galaxy, and that is shining so bright. And that is where the supermassive black hole is located. But the way to actually show that there is a supermassive black hole at the center is what we did was we tried to observe the center of our Milky Way, and we tried to see the orbits of the stars. So as I mentioned earlier, that we measure the mass of the stellar mass black holes by calculating the binary orbits of these stars going around the black hole. We did the same experiments with the supermassive black hole at the center. So here is the experiment where you have really large number of stars that are going around the center, and you calculate the orbit of this star going around, and by measuring how fast it is growing by calculating the time span of the orbit, you can see how much mass is present in the center, which is shown here in this small dot. And when we calculate that mass, it turns out that there is a black hole of 4 million solar mass in the center of our galaxy. So by measuring this orbit of the star around the supermassive black hole in our center, we can see that there is a black hole present there. So this is one of the best ways of discovering black holes in the galaxies. And for this observation, for this experiment, the Nobel Prize was given last year to two experimenters, Professor Andre Ghez and Professor Reinhard Genzel, who were given the Nobel Prize for discovering this black hole at the center of our Milky Way.
Oh,
so I think we can take a few questions about supermassive black holes.
This is just getting even more stellar, pun intended. Abhijeet, in the center of a Milky Way, there is a black hole we never envisioned. So somebody asked a good question. Is it, we'll come to Athansh's question, but is it true that every galaxy has a black hole in the center?
Almost every galaxy has a black hole, yes. There are some galaxies that we don't know whether there is a black hole. The complications are usually from measuring the mass of the galaxy and measuring the mass of the black hole, or trying to understand what is at the centers. In some galaxies, what happens is that the galaxies are also not just isolated. They interact with other galaxies. So you can have a situation where two galaxies collide. Mm-hmm. And when those two galaxies collide, the central black holes also collide. And they form this binary system similar to the gravitational wave system that I showed you earlier. The big supermassive black holes can also form this binary system. And sometimes what happens is that in the extreme turmoil that happens when two galaxies collide, the black holes can get kicked out of the galaxy. So what you might end up is that you have a galaxy which eventually forms after this collision. That galaxy will be there, but the black holes are kicked out. So you can't observe those black holes. So what you end up is a galaxy without a black hole.
Black hole. Okay. And Abhijeet, Athansh has a great question. Is it true that smaller the black hole, stronger it is?
Kind of, yes. In a sense that the gravitational, the main signature of a black hole is what we call the event horizon. That defines the size of a black hole. And that is dependent on the radius, but the square of the radius and the cube of the radius. So because of that, a smaller black hole actually has a much smaller event horizon. So you can get a lot closer to that edge of the black hole without going in. So because you're getting much closer to the edge of the black hole without going in, you will feel a lot more gravity of that. So you will feel a lot stronger gravitational effects without going into the black hole. While for when the black hole is very, very big, the center is much far away from the edge of the black hole, which is the event horizon. So because you're so far away from the center, you often don't see don't feel the effects of the gravitation so far out. So the gravitational attraction of these big black holes can actually feel to be much lower than the very, very tiny black holes.
Oh, wow. Abhijeet, another question. Daksh asks, can a planet survive a black hole?
Yes. In fact, one of the fun things is that if you're far away from the black hole, so let me just come to the misconception slide first.
Okay. So many questions. Yeah.
So let's come to the first misconception that a lot of people have. And that misconception is that black holes are like vacuum cleaners, that they just suck everything in. And no matter how far you are, eventually you will be sucked in. And that's not the case. As I mentioned to you, the Newton's law of gravitation, what does that say? the force of gravitation is proportional to the mass of the two objects and inversely proportional to the radius. So it only depends on how massive the two objects are. So let's say two objects are a star and a planet, or a black hole and a planet, right? And you have these two objects. The force only depends on how massive they are and how far they are. It doesn't matter what the mass is made up of. The star could be made up of diamonds. The star could be made up of feathers. As long as you have 2 kilograms of mass here and 5 kilograms of mass here, they will always have the same attraction. Now, what happens, the difference is that this law becomes slightly complicated when you're really, really close to the object. So when you are really close to the black hole, so the distance is also important for the gravitation. So when you come really, really, really close to the black hole, then you feel the extreme strong gravity of the black hole and you cannot form a stable orbit around it. So you will eventually fall in. But if you are far away from the black hole, that just like normal, for a planet that is far away from the black hole, it will be just like normal going around a star. So if you did an imaginary experiment where you, instead of having a sun in our solar system, you remove the sun and place a black hole inside there in the place of the sun, the planets will just go around as if nothing has happened, because the only thing that matters for us is how much is the mass. So if you just replace the sun with the black hole of the same mass of the sun, the planets will just keep on going around, because for them, they don't care whether the central object that is creating the gravity, it is made up of the star, or if it is made up of neutron stars or from black holes.
All right. So we get that, Abhijeet. So it's basically the distance that matters from the black hole.
Exactly. So what happens is that what we call relativistic effect. So what Einstein had told us, that the space-time is made up of this fabric that is twisted by the gravity of the objects. So this twist of the space-time is felt only in the very, very close vicinity of the black hole. So when you get really close to the black hole is only when you will feel the extreme effects of the black hole.
All right. Okay. We can go ahead with the other misconception slides. Sure. Abhijeet.
Yeah. So I think I have already covered the misconception that our sun could become a black hole. So as I mentioned, our sun is just too small to become a black hole. You need minimum 10 to 20 times mass of the original star to become a black hole. So our sun is just not going to ever become a black hole. So we can not worry about it. So let's talk about things that we don't really know. So the only things that we know so far about black holes are what you see in this cartoon diagram that I have shown you. So a black hole is made up of two things. There is the extremely compact object at the center. We call it singularity, because we think that the mass and the density there at the center has become infinite, and it just becomes so compressed that the twisting of the space-time has become so much that it just twisted into infinity there. So that's the center. That is the main part of the black hole. And the event horizon is the boundary of the black hole. So that is where once you go inside, once you cross this boundary, you can never come back. If you're outside, then the escape speed outside is smaller than the speed of light. So if you're outside of this boundary, you can turn your back, you can turn your engine, you can turn your rocket and fly back away, as long as you have enough petrol to fly. But once you are inside, the escape speed becomes more than the speed of light. So even if you have all the rocket boosters, even if you have all the energy in the world, you just will not be able to turn back. So once you're inside, you're always inside. You cannot come out. So this boundary is called the event horizon. And the radius of this boundary is called the Schwarzschild radius. So these are the parameters that define a black hole. So what happens inside the black hole, all we know is that anything that falls inside the black hole eventually ends up into the singularity and making it bigger and bigger and more massive. That is the only thing that we know. We have no idea what happens inside. There are also complications whether the black hole is just stationary or whether it is spinning. If it is a spinning black hole, then there are even more complications, because then that twists the space-time even in more weird ways. So then instead of forming a single sort of spherical ball-like singularity, you create a donut-like singularity. So like a Medu Vada singularity, where you have a ring structure formed in the center that creates a very unusual shape. But we have never looked inside, because you can never look inside a black hole. So we have no idea what goes inside the black hole and how those things interact. So we really don't know what happens inside the black hole.
Wow. So, Abhijit, many questions came. When you look from the singularity to this Schwarzschild radius, what is there? Is there matter? Because the matter is in the singularity. So, this literally, what is in a black hole? The singularity, and then what?
There is nothing. So once inside, there could be some light rays that could be going around still. So things that have fallen into the black hole, but which have not reached the center yet, you could be seeing those things. You could be seeing a lot of light particles that have fallen in and that are going around, but that have not fallen to the center yet. But there is no actual boundary. So there is no physical boundary there. The boundary is only a mental boundary, essentially.
Yeah, I get that. Okay, all right. Okay, so what could fall in a black hole? A star could fall, a planet could fall.
Anything could fall in a black hole, essentially. Anything that exists in the universe, if you take it too close to the black hole, it could fall in. If you're too far away from the black hole, you're fine.
Yeah, Athansh liked your analogy of Medu Vada. he commented on that. Okay, the other... does the sun orbit around a black hole? Aditi asks.
Not exactly. So our sun is a sort of solar system, is a free-floating system in the Milky Way. So if you imagine our galaxy, which is, let's say, in this spiral shape. So you have this spiral shape. Our sun is one of these small points you see, the small stars in this spiral shape. So it is just going around around the entire galaxy, and it completes a rotation around the galaxy every 200 million years. Of course, there is the central black hole inside the center of the galaxy, but that does not control the entire galaxy. The rotation of stars around the galaxy is actually controlled by the central big shining ball that you see here. That is made up of stars that are, even in total, they're more massive than the black hole itself. So actually the stars in the center, they create the gravity. And there's also other things such as the dark matter inside the overall galaxy. So those are the things that control the motion of the stars in the galaxy. So our sun is technically going around the black hole, but not exactly.
So can a black hole suck up the sun? Can the sun go into a black hole?
No, because our sun is just too far away. So as I mentioned, that the black hole is extremely tiny at the center. It's similar to how a virus is so tiny compared to a human, that it's so far away and so tiny that it does not affect us directly. The sort of gravitational effects that we feel are only because of the 2 or 3 orders of sort of indirect effects. So the black hole has an effect on how many stars are there in this central bowl. So a nice big black hole at the center will attract a lot of stars, forming this big ball of star at the center. We call that a bulge of the galaxy. So in that spherical bulge of the galaxy, there are billions of stars. So a bigger black hole will attract a lot of billions of stars. And those billions of stars will have the gravity to sort of have these spiral arms of the galaxy going around. So our sun is just so far away from the black hole that it will have no effect from the black hole.
All right. Abhijeet, there are many good questions, but you want to wrap up your slides, then we'll do them in the end. Sounds good? Sure.
Excellent. So only a couple of slides were remaining. So the 2 other ways of measuring or finding out these supermassive black holes is this accretion disk that I mentioned, similar to how you have the gas from the stars that is in a binary system that is sucked into the black hole. Similarly, in a galaxy, you saw that the black hole is surrounded by these billions of stars and the gas in the galaxy. So that also forms this accretion disk, and there is energy given out from these north and south poles of the black hole. So not everything that falls into the black hole, but some of the energy is given out in terms of these radiation from the north pole or south pole. And we see those radiation in form of these massive jets that come out of the galaxy. So here in this picture, you see this at the center, this blob, that is actually a massive galaxy the size of our Milky Way. And these are massive radio jets that are thrown out from the black hole. So you can imagine you can line up 30 Milky Way galaxies along the entire span of these jets. So these jets are really, really huge. They are millions of light years in size. And the only objects that can create these kinds of extremely pointed jets, they're almost laser-like in structure. And only when they grow to be very, very big that they sort of start spreading out. So only way you can create these jets is from these supermassive black holes. So when we are observing thousands of galaxies in the universe, we try to look for these structures of jets. And from these jets, we can find hundreds and thousands of black holes in the universe. And of course, the accretion disk is what when we observe the event horizon of the black hole, you saw, all of you must have seen this picture, which was on the front page of every newspaper in the world. What you're seeing in this orange glow, like the Medu shape that I mentioned, that this orange glow is actually the accretion disk around the black hole. And the central black shape in the middle is the effect of the event horizon that you're seeing, that in the center is darkness and it's surrounded by a large amount of light. And what we are observing is this light going around the black hole. So you see this hole in the middle from which no light is coming. And you are surrounded by this extremely energetic light that is surrounding the black hole. So that is how you actually observe these black holes. So this was the first time we had actually made a full picture of the event horizon scale of the black hole. And to give you an example of how big this is, you can see in the center is the size of our solar system. So our sun in the center and the Pluto's orbit around. So our entire solar system can fit inside this black hole. So the black hole that we observe in the galaxy M87, that is so big, it's several times, it's 6 billion times the mass of the sun. So it's so big that our entire solar system can fit inside it. So it's really, really that big of a black hole. So this is how we observe stellar mass black holes in these binary systems in gravitational waves, and looking at these accretion disks and these jets that are coming out. That is how we observe these stellar mass and supermassive black holes. And the last thing that I want to come to are wormholes. And of course, wormholes, we have seen those in a lot of science fiction stories and in TV series and everything. But I don't like it, but I have to disappoint you guys. Wormholes are not real. They are a fantasy concept where you can connect the two black holes together by a tunnel. But to create those kinds of tunnel, you need exotic matter that does not exist in our universe. You need matter and elements that are made up of negative power and negative energy that just doesn't exist in the universe. So wormholes are not real, and white holes are essentially the other side of the black hole that you would come out of the wormhole. So those things don't exist in reality.
Oh, wow. Creepy. This is Tanishka. It is creepy. Really, really. It's imaginary. Yeah. So Avnish has a question. Is the Bermuda Triangle similar to a black hole? You know,
No.
the triangle where all ships would just like disappear and all? No.
Of course. So the Bermuda Triangle is not actually reality. It's a myth. It's something people believe to be true, but it's not real. There are no ships going missing in Bermuda Triangle. It's just something that people believe that is happening. But the reality is that sometimes, because when you are going across large voyages in the ships can sometimes sink. And when they are so far away from any land, there is often a signal missing. And earlier, a few hundred years ago, when the communication was not as good, you did not have GPS signals and so on.
Yes.
There was a possibility of ships going missing, but the ships used to go missing all over the world. Now we have better technology and better things. Ships don't go missing as much as they used to now. So the Bermuda Triangle is not a reality.
Okay, Abhay, you can ask the next question.
Yes. Do black holes become bigger or smaller over time?
Well, the black holes, when they are attracting this mass, so when they pull the matter from the star or from the surrounding gas and so on, that matter eventually ends up towards the center. So black holes usually keep growing and growing and growing until they run out of all the matter. And then what happens is we don't know. So one of the things that has been theorized by Stephen Hawking is this Hawking radiation, where the black holes can give out some kind of a radiation that is made up of some quantum effects that it's really difficult to explain to in simple language, because these quantum effects are very technical and it's difficult to explain how that happens. But there is a theory for some energy that is given out by the black holes. And eventually, in trillions of years, when all the stars are gone, all the gas is gone, the black holes will eventually start losing this energy through this Hawking radiation. And eventually they will start growing smaller and smaller again. But that is much, much longer time span in the life of the universe. But currently, black holes are usually just growing by eating a lot of material from stars and gases.
Okay.
All right. Abhay, last one question we can take. Nishchay's question. Abhijeet, look at the number of questions and we'll take you up on this, that they can email you if they have any questions.
Of course. And we can maybe in few months' time, we can have another discussion.
Yes,
again.
certainly. Would love that. Would love that. Now they will go and read. I'm sure everyone is going to be Googling black holes.
Of course.
All right. Abhay, maybe take Nishchay's question and then we'll wrap up.
Actually, I don't see Nishchay's question.
So he asked about satellites. Do satellites survive a black hole? And when we send a satellite, I mean, how do we know it's not going to go into a black hole?
Excellent question. So we have never sent a satellite to black hole. Black holes are really, really, really far away. Okay. The closest star-like black hole, the stellar mass black hole that I mentioned, that is thousands of light years away. We have never been that far. As I show you in this picture, so the Voyager 1 probe, that is the farthest object that we have sent. And that object is still within the sort of bounds of the solar system. And that is not even close to any of the black holes. It's not even close to the nearest star that is 4 light years away. It has not even crossed 1 light year distance. So we have not sent any satellites anywhere close to any black holes. Most of the telescopes that we have, most of the satellites we have, that are still near Earth orbit. So they're within Earth's distance to the sun. So they are not any far away. So we have never been to any other stars or black holes or anywhere.
So Abhijeet, Ala has a question. Do nebulae have connections with black holes? Nebulae?
So nebulae are a different kind of objects. So nebulae are essentially clouds of gas in the galaxy, which form these nurseries for stars to form. So stars usually form from hydrogen gas and other kinds of elements. So these nebulae are the birthplaces. So you have a lot of gas that is present, and because of that gas that collapses onto itself is eventually how you form stars. So nebulae are essentially where stars are formed. They are made up of gas.
Can a new universe come into existence from the singularity of a black hole?
That's a fantastic question. And similar to the question about what is inside the black hole, we have no idea what is inside, what happens at the singularity. Depending on which theory you believe in and which mathematical calculation you make, you could come up with an equation that tells you, okay, you might form a universe out of the singularity, but nobody knows what happens inside. We have no idea. And until we have an idea, we just can't answer that question.
Thank you, Abhijeet.